Okay. Testing the mic. Is that okay? Thank you. All right. Good morning, everyone.
Good morning.
I hope you could get a little sleep before this lecture. So if you remember, yesterday we did liveness analysis, static analysis that tells you when a variable is dead, so when it's not going to be used any longer. And we used it to implement dead code elimination, so removing assignments to dead variables. And so this morning I'd like to extend this a little bit towards register allocation. So what is a register allocation problem? Well, as you probably know, in your machines there's main memory, which is very big, but kind of slow to access. And then in the processor there are a few registers that can hold numbers or pointers, and whose access is extremely fast, but there are very few of them. Like on an x86, there's maybe 7 available integer registers and 8 available floating point registers. Okay. And so one of the big deals, of compilation is to make the best use of those 7 registers. Okay. And keep in them as many data manipulated by the program as possible. And that's really important to get good performance. So basically, at some point, the compiler places the variables used by the program, and there can be arbitrarily many of them, into the hardware registers, and when it cannot, in memory locations, often on the stack. And of course, it wants to maximize the use of hardware registers. So there's a very naive approach. You look at your program, you pick up the n most used variables, and you assign them to the n available registers, and everything else goes on the stack. But that is very suboptimal, because it is possible to do better when it is possible to have 2 variables that, or more that share a given register, as long as those 2 variables are not simultaneously live. And here is an illustration. So here we have a piece of straight line code. Here we are defining x, using x, and then x dies. And later we are defining y, so y gets live and using it. And as you see, the live range, the interval of time where x is live, is disjoint from the interval of time where y is live. So we can actually rewrite the program to basically use only 1 variable, or indeed only 1 register for x, and then for y. And as long as we don't use both x and y at the same time, okay, this is correct. And so that's what we are going to do. So if you want to do it properly, like in real compilers, we would have to first break complex expressions into elementary computations with some temporary variables to hold intermediate results. And that's because, well, you also want to assign registers for these intermediate results. Okay? And then we would translate imp to some variant, imp prime, that doesn't use variables, but instead the union of registers and memory locations. So that's how it is properly done in real compilers. So just to make it simpler, and we are not going to break expressions, so we will keep some kind of abstract stack to evaluate them, for instance. And we will simply translate from imp to imp. So we will just rename identifiers with a convention that, for instance, the low-numbered identifiers really stand for hardware registers. Okay. All right. So renaming. So assume we've found a register assignment. So basically, a function from identifiers to identifiers. Okay. That is the candidate register allocation. So the program transformation consists of renaming variables. So all occurrences of x become f of x. Then, as yesterday, we'll do dead code elimination. So if x is dead and after this assignment, then we remove the assignment. And there's one more optimization that we can do now. It's called coalescing. If you assign a variable y to a variable x, and it happens that they are both mapped to the same location or register or so on, well, you can just skip this assignment, okay, because it's really f of x gets f of x gets f of y, which is just z gets z, and that is a no operation. So it's called coalescing in the literature. All right, you're with me? But now, what are the correctness conditions in this register assignment? So clearly, not all functions from identifiers to identifier will preserve the semantics of the program. And here's a very simple example. We have this code with 3 variables. X is 1, y is 2, and then x plus y is z. If we map the 3 variables to the same register R, then we get this code. And so this one computes 3 in Z, and this one computes 4 in R. And that's an example of illegal reuse of R, because here we need both the value of X and the value of Y, so they cannot be put in the same register. And so we have to find sufficient conditions over F. And we can actually discover them just by reworking the proof of semantic preservation that we did for that code elimination. Okay, so that's kind of backward. We are starting with the proof and trying to find what we need to know about F for that proof to go through. So we are going to refine the agreement, or to revisit the agreement notion we had. So S1 is a state of the original program, S2 is a state of the transform program. So the original program talks about the variable x, the transform program about the variable f of x, and we are asking that S1 of x is equal to S2 of f of x, but only for live variables. Okay, as you remember, we don't care about the values of dead variables anyway. And then, so these are variants of lemmas that we saw yesterday. So for instance, if let's see, if S1 and S2 agree on the 3 variables of an expression, then evaluating the original expression in S1 is equal to evaluating the renamed expression in S2. And likewise for Boolean expressions. So far, I mean, that holds for any F. Okay, we don't have any side conditions. And again, as before, agreement is monotonic. So if you agree on a big set, then you agree on a smaller set. And as before, still no changes. If in the original program we assign to a dead variable, and in the transform program we don't do anything, agreement is preserved. What is different is preservation by parallel assignment. Okay, so the original code assigns V to X. The transformed code assigns V to f of X, the renamed of X. And that will preserve agreement, but only if, let's read that, only if no other variable Z, that is live after, is mapped to the same location as X. Because if it were the case, so I think I tried to write a counterexample here, but the idea is quite simple. If it were the case, if you have a live Z that is mapped to X, here we are assigning to X but not to Z, so X changes value, Z keeps its value. And here we would be assigning both to f of X and f of Z, right? And so that would be incorrect. But if we have this side condition in red, then assignment is fine. And then we can refine that a little bit for moves. So variable to variable copy, X gets Y. Because in this case, what we are assigning to X is not an arbitrary value, but it's actually the value of Y. And so we can weaken the non-interference criterion by saying basically that it is OK for Y and X to share a register. Okay, so still all other variables, all other live variables, Z different from X and different from Y, should not map to the same location as X, but Y can map to the same location as X. Well, that lemma is true. And this gives us an additional flexibility, which is to assign X and Y to the same location and therefore delete this assignment, okay, even though X and Y can be simultaneously live. And And okay, so these are all the conditions we need over f. Basically, anytime we need to invoke those lemmas, which is essentially when we compile an assignment here, a general assignment here, and a variable-to-variable copy there, those side conditions over f must hold. And there's a nifty way to summarize those various constraints, f of x different from f of y for certain pairs x, y. It's a so-called interference graph. So it's an undirected graph with program variables as nodes and edges between x and y if x and y cannot be assigned the same location. So there will be an edge between x and y if there is one such constraint that must be honored. And so that was invented by Gregory Chaitin in the early 80s. And so Chaitin gave an algorithm to construct this graph, which is basically you do liveness analysis and you scan your program. For each move, you add edges between x and every variable z that is live after the assignment except x and except y. And for general assignments, x becomes a. You add edges between x and every variable z live after except x. So that's the recipe that was in Chaitin's paper. And so if we apply it to our favorite program, which is Euclidean division by repeated subtraction, well, you get that interference graph with the full edges. So, for instance, A and B, let's see, why do they interfere? Oh, yeah, they are not assigned here, but they are live at the beginning. Okay, that's a bad example. B and Q, for instance, interfere because here we are assigning Q and B is live across this assignment. And then I've added another kind of edges, the dotted edge, which is a preference edge. This one is not a strict constraint. It just says that if we manage to assign A and R to the same location, then we could get rid of this assignment, so that would do it better. Okay, so but that's just a preference. It's to get better code, not to get more correct code. And why go to this graph presentation? Well, because now the problem of finding a register assignment reduces to graph coloring. Okay, so just to remind you about graph coloring, so the problem is to color this interference graph and using registers or memory locations as colors. So each node should pick a color under the constraint that two ends of an interference edge have different colors. Okay. And then we have some optimization objectives. So we want to minimize the number, maybe, or some kind of total weight of the nodes that are colored by a memory location. We really want to maximize the use of registers. And we would also like to maximize the number of preference edges that are satisfied, so both ends have the same color. So if you weren't hungover, you would jump on your seat and say, but that's an NP-complete problem. It's extremely costly to find an optimal solution, and yes, it is. The good news is that there are very good heuristics that run in linear time or quasi-linear time. Okay. And for instance, Andrew Appel, who lectured last week, is the author of one of the best such heuristics, the George Appel iterated register coalescing, I think, algorithm. And so this is our interference graph for our example, and this is a valid coloring. I hope you can see the colors. So A and R are both in yellow. They can be because there's no interference edge, and that will even satisfy the preference edge. However, for the other, here we have a clique, right? So we need three colors. So this is yellow, this is green, and this is red for the color impaired of you. And so now if we rewrite our program by putting colors instead of variables, then we get this program. And in particular, we can remove this assignment, yellow equals yellow. And so basically, our program can run with only 3 registers. And I don't think you can do any better, again, because you have this clique here. All right. Now, if we want to follow this approach in a verified compiler that we prove in Coq, well, it looks like we will have to formalize and prove correct a good graph coloring heuristic. So I mentioned the IRC algorithm of George and Appel. So Benoît Robillard, student of Sandrine Blasi in France, actually did his PhD on formalizing this graph coloring heuristic in Coq and proving it correct. And I think in the end it was even more than that. It was about 10,000 lines of Coq. So that's a big proof, and kind of complicated and not terribly interesting, if I may say so. So there's an alternative, which is the so-called translation validation or validation a posteriori. And the idea is every time you compile your program, so you build this interference graph, and then you invoke an external oracle, an external solver, to compute a candidate allocation. And that solver is not going to be approved. Okay, it can be any off-the-shelf graph coloring package. And then, before using it, we will check that this candidate allocation is indeed the correct coloring, that it satisfies the non-interference conditions. And if it doesn't, and we will do that checking with a Coq function that is proved correct, okay? And if that Coq function says no, then we abort compilation, okay? We just tell the user something is buggy in this external oracle. However, if the checker says true, then we know that we have a correct coloring, and so we can prove now that the program transformation is correct. So this is what we are going to do. Oh yeah, and so in general, there's kind of a spectrum in for compiler verification. So if you have a code transformation, so you can try to prove it correct, to formally verify it from A to Z, and this is what we've done so far. But at the other end of the spectrum, you can also leave it completely untrusted. So there's some untrusted code that performs the transformation. And then at every run, you feed the code before and after transformation into a validator, which is some independent algorithm that is going to check that, to try to check that both codes are semantically equivalent. And if it says yes, compilation continues. If it says no, that's a bug in the compiler, so we abort compilation. And actually, if we just prove correct the validator, then we get strong guarantees that the compiler will basically never generate wrong code, okay, but it can abort more often. And so that approach, translation validation, was introduced by the late Amir Pnoueli. And originally, so he did that for reactive languages, kind of data flow languages that are not Turing complete, and for which actually this equivalence problem is fully decidable using model checking techniques. So for more complicated languages, Turing complete languages, so in general, there is no complete validator. But it is possible to write validators that are perhaps specialized to a particular transformation. Okay, so they know something about how much those two codes differ, and that are complete in practice. So that's a pretty neat approach, and a former PhD student of mine, Jean-Baptiste Tristan, actually developed and verified such validators for several advanced optimizations. And so for graph coloring, the approach I just outlined is kind of intermediate. So the transformation itself is proved correct, but it calls into an untrusted solver for graph coloring, and whose results are checked by a trusted checker. Okay, so it's kind of a mix between the two approaches. Okay, and so, well, it's easy to write actually a Coq Boolean valued function that takes a candidate allocation, a command, a set of variables live after, and returns true if all expected non-interference properties are satisfied. And let me demonstrate. All right, so let's see, can you see? Yes. So basically, yeah, so that's in file regalog.v, and so the first part is just what we said. Here is a candidate allocation f in a section. This is the renaming into arithmetic expression. This is renaming into Boolean expressions. This is the transformation for a command that does the renaming of variables, eliminates dead code, okay, like if we are assigning to a dead variable, then we return skip, and does the coalescing. So if the right-hand side is variable y, and if x and y are assigned the same location, then we skip. Otherwise, we compile an assignment. And I think everything else is exactly as in dead code elimination. And now also for semantic preservation, so we have this notion of agreement revisited that we described. The various properties of agreement and agreement under updates that we saw in the slides. And this is the checker. So this Boolean valued function, which is defined by recursion over the command. And so all the interesting constraints come from assignment, as usual. And for instance, if this is an assignment x gets y, then we demand that for all elements of L, either z is x or z is y, or it is not the case that f of z equals f of x. All right? So this is really a Boolean expression that computes the truth value of the various conditions we've seen before. Okay, so yeah, we have this case for assignment, this case for variable to variable assignment, this case for general assignment. This is a case where we are dead anyway, and then it's just well, some kind of conjunction of the correctness conditions for sub-expressions. Okay, and again, this is completely computable, right? It returns a bool, and it's a coq function, so it always terminates. And then there are some boring lemmas that show that if the function says yes, then indeed the non-interference conditions, which live in prop, not in bool, hold. So yeah, that's one of the slightly painful aspects of coq, that there's no automatic injection in a way from Booleans, so computable Booleans, into truth values of the logic. But well, we can live with that. And then we can prove semantic preservation for dead code elimination under this additional hypothesis. Okay, so we need agreement between the states. Okay, let me read that again. Consider a command C that executes, transforming state st to state st prime. Consider an initial state st1 that agrees with st under variables live before. And further assume that the allocation f is correct for C and for L. Then there exists a state st1 prime such that the transformed command started in st1 terminates in st1 prime. An agreement is preserved. Okay, and the proof is a slight extension of the proof we saw for dead code elimination. So I'm not going to go into it. There's one case for each reduction rule and a bunch of subcases for assignment. Okay. So a subcase whether x is live or dead, a sub-subcase whether we have a move or not, a sub-subcase whether the move has been coalesced or not, and this is the general assignment case, not a move, and this is a case where x is dead. And everything else is kind of routine, so I'm skipping all that. And likewise, we can also extend this result to diverging executions, which are also preserved. And let me come to a few examples. Hello? Hello? No, it's making progress. It's just early in the morning, but all right. So let's do first examples with a trivial allocation, the one that doesn't rename anything. Okay, so we are not going to get very good code, but the point is that we are getting actually dead code elimination, exactly what we did yesterday. And so of course this is a correct allocation. This is a correct allocation, and if we apply it to our Euclidean division program, well, we get oh yeah, and saying that we are only interested in R, then as before, we get that Q, computations over Q are eliminated. Okay, but now let's have a look at a non-trivial allocation. So this one is going to collapse variables R and A into a single variable. And let's check if it is correct. Yes, Coq says yes. So what does it do? So not only it removed all computations over Q, but it also removed the assignment R becomes A. And now, because it's just using the same register, which is called A, to do the computation. Okay.
Is there anything before that line? The while? Is there a skip?
This one?
No, in the lower pane.
Oh, sorry. Yeah, let's see. Yes. So we get our two skips, meaning that those two assignments were removed, and then the loop.
Very good. Works, yay!
Of course it works. It's been proved correct. So. Yeah. And so now here is an example of a wrong allocation where we try to collapse R and B in the same variable B. And then our checker says wrong. And you can probably see why. Yeah, because for instance here, or even in this comparison, we need both the value in R and the value of B, and they are distinct in general. Okay, so well, just to wrap up. So now we assume that there's this external solver based on graph coloring, perhaps, that will return that candidate allocation. Okay. And now we can write our register allocator as a partial function, so it's going to fail sometimes, which just calls the heuristic, checks that the allocation is correct. If so, transforms the program, and if not, signals an error by returning node. All right, so yeah, I think that concludes what I wanted to tell you about register allocation. Oh yeah, so these are the correctness theorems that we already saw in the Coq development. And yeah, that's it. All right, so you have questions about this part before we move on to other topics? Yes?
Did you have reused the expected version of the proved graph coloring algorithm?
Personally, no. I'm pretty sure Benoit Robillard, the PhD student, did that and connected it with the concert compiler. And you're going to ask about performance or quality of allocation. If I remember, so the extracted version was somewhat slower than the handwritten version, but that's because the handwritten version was using imperative data structures. But it wasn't that much slower. And I think, well, the quality of allocation was maybe a little lower because, again, the unproved code contained some additional heuristics, but not that many. Yes?
So, my experience is there's never enough registers.
Uh-huh.
So, do you do any kind of analysis to detect which variables are used inside of the tightest inner loops?
So yeah, that's a good point. That's typically the kind of heuristics that a good graph coloring allocator uses. So I think in Concert, I'm not doing that yet, but I am considering, I am giving priority to variables that are used more often. And yeah, there are some heuristics that basically give much more weight to variables that are used often. Yeah. All right, so let me move on to the next part of the lecture, which we will start this morning and finish this afternoon. It's static analysis, again, viewed from a more generic or more general standpoint. So let me do some more introduction to static analysis when we started yesterday. If you remember, the point is to statically infer properties of a program that are true of all executions. So for instance, at this program point, we have these inequalities between variables x and y, and the pointer p is never the null pointer, for instance. So there are two important words here. The first is infer. So the idea of static analysis is that no programmer intervention is required. In particular, we are not asking the programmer to annotate the source with preconditions, postconditions, loop invariants, and so on. And then the second important word is statically. So we don't know the inputs to the program when we analyze the program. The analysis must always terminate, and the analysis must run in reasonable time and space. And so here are some more examples of properties that can be statically inferred. So of course, not all properties can be statically inferred because you run into undecidability issues very quickly. But and in general, those analyzers are also conservative or incomplete. But anyway, so here are some useful properties for which we know how to analyze them with sufficient precision. One is whether a variable is equal to some constant, and that is used for constant propagation. Oh yeah, so all those properties are properties of the value of a single variable. So it's called value analysis. And then on the next slide, there will be properties of several variables. And that's called a relational analysis. So for value analysis, we have, for instance, whether a variable is equal to a compile time constant, whether a variable is 0, positive, or negative. So that's the analysis for signs. Whether a variable is within a given interval of integers or even floating point numbers. Whether a variable is equal to n1 modulo n2. So that's congruence analysis. And sometimes it's useful to know that a variable is equal to 0 modulo 4, for instance. Then there's pointer validity. For instance, this means that if P points to an array, indices n1 to n2 of this array are valid, are within bounds, okay, so are valid memory locations. And then there are properties for aliasing or non-aliasing of pointers, like for instance, P is different from Q. This is non-aliasing. Or P points to X, which is more like aliasing, so we know what P can refer to. And often we have a set here of variable. P points to X1 or X2 or X3. So that is value analysis. And now relational analysis gives more information, but is also much more costly. Typically, you have linear inequations between the values of several variables, x1, the xi's. So the ai's and the c's are constants determined by the analysis, generally rational constants. So this is also called polyhedras because, well, if you have a conjunction of such, so basically it says that in a multidimensional space, your point lies on one side of an hyperplane. Okay, and now if you have several such inequations, then you have several hyperplanes, and that delimits a polyhedron. So that's quite powerful, also quite expensive to compute. So there's a simplification where you take the coefficients to be 0, +1, or -1. And it's called octagons, because in 2D dimension that gives you octagons. And this one is cheaper to compute and very useful, actually. Then you can have so-called Herbrand equivalencies, which are just equalities between symbolic expressions involving variables. Okay. And then there's even analysis for so-called non-functional properties. So properties that don't talk about values of variables, but may talk, for instance, about memory consumption or worst-case execution time. And we can use the results of those static analyses for optimization, of course. For instance, to apply algebraic laws when their conditions are met. This is an example we saw yesterday, sign division by 4, which becomes an arithmetic right shift by 2. And that's only correct if the analysis can prove that x is positive. So this is constant propagation. Replace x plus 1 by 1 if you happen to know that x is 0. Then you can do a lot with array on pointer accesses. So for instance, here we are assigning into a of I, then into a of j, then reading back a of I. And if we know that a is not equal to j, then we know that what we are reading here is what was written there, and so we can optimize this into x equals 1. And likewise, if we have a store to a pointer followed by a load from another pointer, and if we know those pointers are distinct, then we can do the load first and the store second, which is generally good because loads have latency, take some time to complete. And then there's even automatic parallelization, typically for Fortran codes, for loop nests. So if you have, for instance, 2 loops that are executed in sequence in your source code, and you analyze, and you can determine the polyhedra of a polyhedra that contains all points that are accessed by that loop, and all points that are accessed by this loop. And if then you can check that, you can see that those 2 polyhedra are disjoint. Then you can run the 2 loops in parallel because they don't access the same memory location, so there's no race condition. And so that's a really important trick in parallelizing compilers. But these days, basically the need for advanced optimizations really drove the technology of static analysis in the 70s and 80s. These days, advanced static analyses are also more and more used for verification. So basically, to establish properties of soundness properties of your program. So not all properties, of course, can be automatically checked by static analysis, but still, the results of a static analysis can be used to prove the absence of certain runtime errors, for instance. For instance, if you have an integer division, and you would like to make sure that it cannot fail at runtime as a division by 0, well, if you do interval analysis, and you have an interval for b that does not contain 0, then you can conclude that the program is safe with respect to that division. And if you cannot show that, then your tool can signal an alarm, okay, and tell the programmer something is fishy here, please have a look. And likewise for an array access or some pointer arithmetic like this, so if you know that this range of indices for p is valid and that I is in this range, then this is a safe memory load. Otherwise, it could fail, and so you may want to signal an error, to signal an alarm, sorry. So alarms are not necessarily errors. Let me display that to you. So here we have those trajectories are the real executions of the program, okay? And there are several because they depend on the initial input. This red zone is when the program really crashes, device by 0, or there's a segmentation violation or whatever. What static analysis does is basically to bound, over-approximate these concrete behaviors by a bigger set in green. And so if that set in green is disjoint from the red region, then the program is safe, okay? And there's no alarm reported, and we know that the program cannot run into the red zone. Of course, now we can have true alarms or false alarms. So this is a true alarm. The real behavior really runs into the red zone, and this is caught by the analysis. And this is a false alarm. Actually, the program gets close to the red zone but doesn't hit it. However, because our analysis is imprecise, for instance, it uses rectangles, okay, then we have an intersection with the red zone. So that's a false alarm. And it's not nice to have too many false alarms because then programmers no longer believe in in what your tool says, okay? And say, oh, it's crap. I'll go back to my usual ways of programming. And so, and that motivates more and more precise analysis. For instance, if instead of rectangles we use polyhedras, right? Then the false alarm can go away.
But your analysis takes longer.
Yes, indeed. Okay, so the kind of properties of safety properties verifiable by static analysis. So that includes, as I said, the absence of runtime errors, like for arrays or pointer, no out-of-bound accesses, no dereferencing of the null pointer, no accesses to a dynamically to a block after it's been freed, Possibly, yeah, that the alignment constraints of the processor have been respected, that there's no division by 0, that signed arithmetic, for instance, doesn't overflow, because in C it is not specified what it does in this case. For floating point numbers, well, it is specified actually what happened with overflows and so on, but many engineers would like to know that, for instance, there's no overflow in the arithmetic computation, so no infinite results. And likewise, no undefined operations, which translate to not a number results. And maybe even no catastrophic cancellations. So I'll explain that on the next slide. And you can also get intervals of variation for the program outputs, and that can be interesting to know as well. So floating point. Floating point is a complete mess because, well, it looks like real numbers, but it's not real numbers. Floating point numbers have a limited range and have a limited precision. Okay, and so every operation actually computes the result exactly and then rounds to the given precision according to well-specified rules. But still, those rules are a bit surprising sometimes. So, for instance, if you have x and y that are floating point numbers, single precision in this interval, so x is slightly above 1 and all the way up to 2, and y is between 0.5 and 1. And if you do 1 divided by x minus y, so it happens that x minus y cannot be 0, even in single precision floating point arithmetic, and so this division will never produce an overflow. However, if you do x squared minus y squared, okay, then because of the limited precision, you can indeed get 0 here and an undefined result. Because by floating point rounding, x times x is actually in the interval 1, 4, because if x is equal to this and you take the square, then it rounds down to 1. And so the difference can be 0, okay? And if you have a good floating point analyzer that does interval arithmetic taking rounding into account, it will tell you. Okay, so that's pretty neat. Okay, and so how do we do static analysis? Well, there are plenty of ways, but there's a fairly generic one called abstract interpretation that I'm going to illustrate and even implement in Coq with you. And the idea of abstract interpretation is quite simple, actually. The idea is that the analyzer is going to execute the program, but only not with the standard semantics. With the non-standard semantics that doesn't compute over values, integers, pointers, strings, but over abstract domains of the desired properties. For instance, for interval analysis, we are going to compute over basically those assertions that a variable belongs to an interval. And also, when there's loops or conditions, okay, because it's an abstract semantics, it's not the most precise concrete semantics. In general, the analyzer doesn't know whether the condition is true or false. So it's going to over-approximate and say, well, both branches can be taken, okay? And then typically it will take some kind of union of the possible results for both branches. And there are various tricks to ensure that the abstract interpreter always terminates. So yeah, a little historical note. So that approach was invented and promoted by Patrick Couzeau and Radia Couzeau in the mid-70s. And for about 25 years, it remained as basically a nice piece of theory that kind of unifies earlier approaches to static analysis, like data flow analysis, but with no practical application whatsoever. And since about 2000, so there have been very successful static analysis tools based on abstract interpretation. So one is Astray, which is used at Airbus to show the absence of runtime errors of the kind I showed in control command codes, like the fly-by-wire system of the 340 and 380 airplanes. At Microsoft, there are several tools that use static analysis, and one is really based on abstract interpretation. It's called code contracts. It's basically C# where you can put assertions, and there's a checker that will, well, statically checked for undefined behaviors, and also trying to prove those, to establish those invariants. And it's based on abstract interpretation. The code name of this, the internal code name for that code contract product is Clouseau. Okay, so and so here are two examples. And so let me tell you a few words about the orthodox presentation that you could find in the papers by the Clouseaus originally. And I think it's not the best presentation, but so the orthodox presentation is in two steps. First, you define a so-called collecting semantics for your language. And it's an operation, it is a semantics that is going to describe not just one execution, but actually, well, it's going to summarize an execution in the following way. At each program point, it's going to collect all possible concrete states that can occur. So for instance, this is a little loop that computes a power of 2, okay, with a while loop. And so originally, x and y have only one value, but since this loop can execute up to n times, so here we have n possible values for x and y at each program point. And then when the loop terminates, we have only one. Okay, so that's highly non-computable, of course. And it's just a mathematical definition. No static analysis tool is going to attempt to compute these sets exactly. And then you use a Galois connection. So again, that's a big, scary word, but it's just the idea that so you have your concrete execution states, and then you have abstract states which are ordered, and the ordering means I contain more information than. And there are two functions that relate sets of concrete states with abstractions. So one is the abstraction function, alpha, and the other is a concretization function, gamma. And it's best illustrated by an example. Say our abstract states are products of intervals, so rectangles, right? And this is several concrete states. So each point is a concrete state, a value for x and y. And abstraction might, for instance, compute this rectangle, well, these two intervals, and concretization will concretize it into all points that satisfy those intervals. So basically, this rectangle that contains all the red dots. And so there are a few, very few sanity conditions that those two functions are monotonic, and some kind of, well, if you apply alpha then gamma, then you get something bigger, okay? So here we had a small set of points, and here we have a bigger one. And also the other way around, if you start with an abstraction, concretize it, and re-abstract again, then you get maybe the same abstraction, or maybe something slightly more vague, okay? But nothing more precise. And then, once you've decided on this Galois connection, then you can start to compute the abstract counterpart of the operations of the language. So, for instance, if your language you have integer addition, okay, then in your domain of intervals you can define an addition, so in the abstract domain, and the definition is canonical. It is the abstraction of the set of n1 plus n2, where n1 is in the concretization of this abstraction and n2 is the concretization of that abstraction. Okay, so that's the canonical definition, and from there now you can calculate. You plug in the concrete definitions of alpha and gamma, and you rewrite, and you rewrite, and you rewrite. So Clouseau's papers contain dozens of pages of derivations like this, and in the end, for instance, you get for the sum of two intervals what you would expect, but there are operations that are more subtle. And the good thing about this approach is that this definition is sound by construction, just because of those silly properties of alpha and gamma. And it's even optimally precise for this particular choice of alphas and gammas. So that is a nice thing. You have to work those calculations, but in the end, you have a lot of confidence in the result. However, this is extremely painful to formalize in a proof assistant like Coq. And in particular, because the abstraction function is generally not computable, and proof assistants don't like non-computable functions. And actually, for advanced domains, alpha is generally not uniquely defined, so that's even worse. Yeah, for complicated domains, there's in general no best approximation for a set of points. There might be several incompatible ones. So forget about this alpha stuff. And now, gamma, forget about the fact that it is a function, okay? Just say that it is a predicate, okay? All we need to formalize is the fact that a concrete point x is in the concretization of an abstract point y. And so that's a concrete predicate that relates a concrete thing and an abstract thing. And actually start looking a lot like a typing judgment, for instance, okay? A typing judgment, you say a term belongs to a type, all right? And the type is some form of abstraction of the term. Okay, so if you keep that intuition in mind, that might help. And then, well, can we calculate the abstract operator? So again, a tool like Coq is pretty bad at equational reasoning and those kind of derivations where you calculate from a spec a definition. But then you can just guess the definition and prove the soundness of what you got. And you may also forget about proving optimality and focus on soundness only. So this is what we are going to do now. We're going to do an abstract interpreter in Coq. And actually, I'll switch to Coq very quickly. And since we are aiming for something that is kind of general or can be used with several abstract domains, so we are going to use the module system of Coq. So our abstractions will be specified as modules, will be defined as modules and specified as module interfaces. So there will be one which is value abstraction that we will use to abstract integer values, because this is imp, there's only integer values, and one for the state. And those interfaces follow the same pattern. There's a type T of abstract things, abstract values, abstract states, some predicates that correspond to gamma, so whether a concrete thing satisfies an abstract thing, belongs to an abstract thing. Then there are abstract operations, like arithmetic operations, get and set operations for stores, and soundness properties. So here we go. Okay, so for instance, this is a specification of value abstraction. So there's a type of abstract value. There's this V-match predicate that says whether an integer belongs to the set represented by the abstract value V. There's a natural order about abstract values, which is inclusion. Okay, so V1, an abstract value V1 is less than or equal to V2 if any n matching V1 also matches V2. Then, in general, this is not decidable, but we will use a Boolean function that approximates that relation. So if it is true, then the relation holds. Maybe if it is false, we don't know. There's a way to inject integers into abstract values. There's a bottom element, which is the empty set of integers. There's a top element, which represents all integers. There's a join, which computes an upper bound. So morally, it's a union, if it were the least upper bound. Maybe it will be slightly over-approximating. But still, if a value is in V1 or V2, then it must be in its join. So these are the abstract counterpart for the arithmetic operations. So abstract add, that takes two t's, returns a t with the property that if n1 is in v1 and n2 is in v2, then their concrete sum, n1 plus n2, is in the abstract sum, v1, add v1, v2. And that's all for the moment. And similarly for states. So state abstraction is built on top of a value abstraction, and morally it is finite maps from identifiers to abstract values. So there's a get and a set operation, okay, to look up or to update the approximation of an identifier. There's a matching relation, and there's a bottom, and there's a top, and there's a join, okay? So we will see later how we can instantiate those interfaces with some concrete domains. But for now on, let me show you the generic analyzer we can build on top of that. So let's see, do I have slides? Yes. So given a value abstraction and a state abstraction, then we can define an abstract evaluator for expressions. which looks a lot like the concrete evaluator, only it uses the operations from V, the value abstraction, and S, the state abstraction. Okay, and this is completely canonical. I mean, if you have an integer, then you inject it as an abstraction. If you have a variable, you look up its abstraction, its approximation in the store. And for arithmetic operations, you combine abstractions. Okay, it's really a no-brainer. And the abstract interpretation of commands is a little more interesting. So this is a function that computes the abstract state after executing command C if we start it in an abstract state S. Okay. And for instance, if it is skip, then the final abstract state is S. If it's an assignment, then we update the approximation of X found in S with the abstraction of the expression. All right. The set of all possible values that this expression can take, if you want. For a sequence, well, we just compose the abstract interpretations of C1 and then of C2. If it's an if-then-else, yeah, this is the first interesting case. If it's an if-then-else, then in general, we don't know whether B is true or false. So this afternoon, we will do better. So we are going to abstractly interpret both the then branch and the else branch, and then join the resulting final states. Okay, so take some kind of union between the set of possible final states. And for a while, again, we are going to take a fixed point, of course. So we are going to compute an abstract state, which is a fixed point of that operator. So basically, we want the, let's see, what am I saying here? Yeah, so if S prime is the abstract state before entering the loop body C, so in the first iteration, we can have S prime, well, we enter with S, so S prime must be no more precise than S. But then if we've done at least one iteration, then we are now in abstrinterp S prime C, and that must be no more precise than S prime. And so again, we are looking for a postfixed point S prime that satisfies this inequation. And we do that by a fixed point iteration, as we saw yesterday. And then we have soundness results, which are kind of canonical as well. So for instance, for the evaluation of expressions, we say that if we have a concrete state ST that matches the abstract state S, and for all expressions, the concrete evaluation of A in ST matches the abstract evaluation of A in abstract state S. And likewise for a command, if we have an execution, concrete execution of C from ST to ST prime, and ST matches some abstract initial state S, then the final state ST prime matches the final abstract state computed by abstrinterp. And these are really easy structural inductions on A and C. So let me show you a little bit of the cog development. So again, we need to compute fixed point. And for reasons that should be obvious to you now, I'm going to use the engineer's approach. So not trying to prove termination and the existence of a perfect fixed point. So again, we just iterate function until we get a postfixed point, or until we run out of fuel, in which case we return the top element of the domain, okay, which is always safe. So this is the abstract interpretation of arithmetic expression I mentioned. This is the abstract interpretation of commands. This is a soundness claim, and again, it's, as you see, quite a simple induction over A, just using the hypothesis we made on the value abstraction. And for commands, it's again a very canonical induction on the evaluation derivation. Yes, please.
How do we know that the fixed point we approximate with that engineer's approach is actually over?
Well, we can prove that.
Over approximates, I mean to say.
Yeah. So why is it? Well, because this lemma holds. So f of fixed point S is below fixed point of S. So it is a post-fixed point, actually. But that's all we need for soundness. And why is it the case? Well, basically, we are starting with bottom and, Well, we stop in one or two cases. Either we were lucky, we have an S, and such that f of s is less than s, okay? And so that must be true. Otherwise, we are unlucky and we run out of fuel, and fixed point is top, but then everything is below top. F of top is below top, okay? Top is always safe, but it doesn't tell you anything interesting about your program, of course. And indeed, here we don't even have to assume that f is monotone, for instance. It's really, well, if we are lucky, we get a good fixed point. Otherwise, we get top. And again, this afternoon, we'll see how to do much better. All right, so this is a soundness claim. And now let me go back to slides for a second. Now let's instantiate this infrastructure. Okay, with some examples. So that's a simple example of state abstraction, which where abstract states are morally finite maps from idents to v.t. So identifiers to value approximations. Identifiers that are not in the finite map will be by default mapped to top. Okay, we need a computable representation. So we can't really use just functions from identifiers to v.t's because, well, some operations, like whether a function is below another one, cannot be decided. So this is a finite representation that is convenient, and then we need a special case for bottom, which means that all identifiers are mapped to bottom. And this is appropriate for all non-relational analyses. It's not going to record properties involving two variables, but it's going to record any property involving one variable. And this is a very simple abstract domain. It's for constants. So it is a flat lattice of integers. So there's a bottom, which is the empty set. There's a top, which is all integers. And then there are singleton sets. Okay, and it is ordered this way. And there's an obvious interpretation for operations. For instance, for plus, bottom plus something is always bottom. Top plus something is always top. And the sum of two singletons is a singleton of their sum. Okay? And so let's have a look at what it means in Coq. Yeah, so this is the implementation of the state abstraction. So as I said, an abstract state is either all identifiers are bottom or all are at top except those in this list. And since identifiers are integers, we can use positional notation. And then follow some extremely boring code that works with lists of approximations. So let me skip that altogether. Good thing we can reuse it for several domains. And it goes on and on and on and on. It feels like a Kuzo paper. And some more. Okay, here we are. So this is the value abstraction for constant propagation for constants. So again, an abstract value, it is a bottom, inch, or singleton of some natural number, or top. And matching, for instance, of a concrete value, well, nothing matches bottom, everything matches top, and n matches inch of m if and only if they are equal. And then, so this is a BLE, the Boolean less than or equal condition. It's soundness proof. Then this is the injection of a constant into an abstract value. It's proof of soundness. This is the bottom, proof of soundness. The top, proof of soundness. The join, which takes a little bit of work, proof of soundness. This is kind of a generic operator to interpret binary arithmetic operations. So you see I parameterize it over f, and then I will instantiate with addition, subtraction, multiplication. General proof of soundness, instantiation for addition, for subtraction, for multiplication, and I'm done. Oof. Okay, yes, I retract. And so now that's the magic of modules and functors. We can instantiate our generic analyzer over those domains. So for instance, we first instantiate the state abstraction, which is a functor, parameterized module, by the domain of constants. That gives us a state abstraction appropriate for constant analysis. And then we instantiate our analyzer over this domain of value and that domain of states. Okay? And now I think we're going to run some examples. So this is a sample program, kind of silly. Initialize x to 0, y to 100, z to their sum, and then we do a little loop where we change x and y. And now if we compute the result of the abstraction, we run the abstract interpreter, starting with top, so undefined in any initial state. And we get this abstract state for the final state. So let me decrypt that for you. So it says that all variables are mapped to top, except variable number 0, which is x, which is top, all right? Variable y, which is 1, which is top, and variable z, the second variable, which is int of 100. So at least we know that z is still 100 at the end, is 100 at the end of this computation. Well, it's not very hard to see, all right, because z is not modified by this loop, and it was initialized as the sum of x and y, and at those points we knew that x was 0 and y was 100. But still, we've been able to propagate that fact quite easily. Okay, let's see. Do I have other examples? No. However, I have a 4-star exercise for you to do on your plane back home, for instance. What about defining a value abstraction for parity analysis? So we want an analysis that tells us whether a number is even or odd. Okay. And of course, there's also a top, where it means we don't know whether it is either or odd. And well, there are arithmetic rules, okay, like the sum of two even numbers is even, and even plus odd is odd, and so on. So it's not too hard. Things get ugly with subtraction, but that's a problem with Coq. So you know that subtraction between natural numbers in Coq is kind of weird, because if you subtract 10 from 2, for instance, well, it is 0. It is actually defined, but it is not what you would expect, because these are natural numbers. And so odd minus odd is not even in general. Sorry, it's the other way around. Odd minus even is not always odd, because 1 minus 10 is 0. Okay, so, but well. But apart from those quirks, okay, this domain is not too hard to write, and you may want to give it a try. All right, let's see, do I stop here for this morning? Yeah, I think I will stop here. Yes, and take questions.
Go back one sec. Why is the bottom plus x and bottom? Shouldn't it be x? Because otherwise, bottom plus and top is bottom.
Yeah, you're right, it is ambiguous what bottom plus top is. But the idea of bottom is that it's the empty set of values, okay? So if at some point in your program you do x plus y and the static analysis of x is bottom, then it really means that this part of the code is unreachable. This part of the code is unreachable because x, the value of x ranges over the empty set. That's what the analysis says. Yeah, let me write that. Okay, so at some point in your code you do x plus y. And your static analysis says that x sharp, the abstract value of x, is bottom. So that, by soundness of the analysis, this really means that x belongs to the empty set. The concrete value of x, sorry, s of x, let's say, belongs to the empty set. So that really means that this part of the code is unreachable. Okay. And so basically you could take anything as that result, but bottom is kind of the most precise. And you're right, if you have bottom plus top, that should be bottom, I guess, again, because that's the most precise. Please?
How, in terms of just engineering, how difficult would it be to extend this from singleton sets to intervals?
We'll do that this afternoon. Just as a teaser. So it is not really difficult to define well, it is a bit more difficult, but not too difficult to define the abstract operations over intervals. But then the big problem is finding fixed points that are sufficiently precise, yet don't take forever to compute. And for that, we will use widening and narrowing. How's that for a teaser? More questions? Okay, thank you.